What's up, my pre-calc people? In this video, we're going to talk about polar coordinates and trigonometry. In this video, we're going to learn exactly what polar coordinates are, how to graph polar coordinates on a polar plane, how to convert rectangular coordinates to polar coordinates to rectangular coordinates, and even how to look at complex numbers through the eyes of polar coordinates. All right, so let's get ready to dive right into it right now. First, we have to know about the rectangular Cartesian plane. This is the grid coordinate system that you guys have been working with, well, probably forever. This is where we have our standard XY plane. And we have a coordinate like 1, 2, and that tells us to go right 1 and then up 2. Or if we have a coordinate -2, -3, we go left 2 and down 3. We all know the rectangular plane, which also knows the Cartesian plane, and it's all, well, really easy. We've been working with it forever. In that plane, we could graph functions. So we have x as our input and y as our output, and that function creates a bunch of points. Put all those points together and we get a cool curve. All right. But now we're going to switch gears to a brand new coordinate system called the polar coordinate system. Now, the polar coordinate system is based on a grid of circles centered at the origin, which we call 0 or O. Now, we also look at lines through the origin. Now, polar coordinates are defined as an ordered pair r, theta, such that the absolute value of r represents the radius of the circle on which the point lies. And theta represents the measurement of the angle in standard position whose terminal side includes the point. Now, I know that definition might be a little bit confusing, but let's take an actual look at a polar coordinate plane and understand how a point r, theta tells us where we fall on that polar coordinate plane. Here we see that polar coordinate plane. Notice that it's made up of a bunch of circles. Every circle has a radius starting at 1, 2, 3, 4, 5, 6. It goes on infinitely. Now, we could also have a decimal amount of radius as well. It doesn't have to be a whole number, so you could have a circle of radius 0.5, 0.6, 1.3, 2.3, 3.9, what have you. So the r value in our coordinate is, it tells us the radius. The absolute value of r tells us the circle that our point must fall on. So if we have an r value of 4, we got to fall somewhere on that circle of radius 4. If we have an r value of 1, we got to fall somewhere on that circle of radius 1. Now, theta tells us where our terminal side is for our angle. All angles start in standard position. Positive angles move up in a counterclockwise direction. Negative angles move down in a clockwise direction. Now, all of the lines that we see in this coordinate grid just represent some of our angles. So we see pi over 6, pi over 3, pi over 2, 2 pi over 3, 5 pi over 6, pi, and so forth going all the way around. We could also go backwards, negative pi over 6, negative pi over 3, negative pi over 2, and so forth. But again, those are just the nice angles that we know and love from the unit circle, but of course, any angle measurement could fall onto this polar plane. Now, how do we know where our point is? Well, we have to look at both the r and the theta. The r tells us the circle that we are on with that radius, again, absolute value of r, and the theta tells us where that terminal side intersects that circle so that we know where the point goes. Now, the only thing that gets a little bit tricky is if we have an r value that's negative. So once we have an r value that's negative, we first have to locate that circle. Okay, that's good. Then we have to find the angle theta. Once we locate that angle theta, we don't put the point at that intersection point with that radius. Because it's negative, that's going to tell us to reflect it all the way across the origin, all the way across to the ray opposite of theta. That can be a little bit tricky, and generically speaking about it, doesn't always make a ton of sense, but once we start looking at these examples, I think it'll make a lot of sense. So now that we understand the basics of the coordinate plane for polar coordinates, let's look at some examples of how to graph polar coordinates in that polar coordinate plane. In this first example, we see a polar coordinate of 2, pi over 6. So the 2 is the r value and the pi over 6 is my theta. So the r value of 2 tells me that my radius must be 2. It's actually the absolute value of 2, which is 2. That means my radius is 2. So I'm somewhere on that circle of radius 2. Now, where am I depends upon the angle that's measured in standard position. So pi over 6 measured in standard position would be this angle right here. And we are at radius of 2, so our coordinate point is right there. Pretty simple. So again, it's on a circle of radius 2, and it's at an angle measured in standard position of pi over 6. All right, this particular problem wants us to look at the polar coordinate 3, pi over 2. So again, 3 is my r value and my angle theta is pi over 2. So I'm going to be on a circle of radius 3 and I'm going to be at a position of pi over 2, which is going to be right there. There it is. How easy is that? So again, it's on that circle of radius 3 and it's at an angle measured at pi over 2. In this example, we are at an r value of 2.5 and an angle of 5 pi over 4. So first, our radius is going to be at 2.5. That's going to be somewhere right exactly in between 2 and 3. And the angle is 5 pi over 4. So all I got to do is find that angle measured in standard position. So 5 pi over 4 is going to be somewhere across this terminal side right here, down there at 5 pi over 4 in quadrant 3. And that angle is going to be, again, the radius of that circle is 2.5. So we're looking at 1, 2, 2.5 is about right there. So there is that polar coordinate 2.5, 5 pi over 4. And here's an example with a negative angle. So again, first my radius or my r is 1 and my theta this time is negative 5 pi over 6. Well, again, negative angles just start downward from that initial side, going in a clockwise rotation. So again, my radius is 1, so I'm on this inner circle here of radius 1, and negative 5 pi over 6, just got to count. Here's negative 1 pi over 6, negative 2 pi over 6, negative 3 pi over 6, negative 4 pi over 6, negative 5 pi over 6 is right there. So here is that point that's on a circle of radius 1 to an angle measured at negative 5 pi over 6. Pretty easy, not too bad. Now, you could start with the r or you could start with the theta, right? We're so used to with x and y coordinates having to feel like we have to start with one or start with the other. No, there is no independent or dependent variable here. It's you could start with the angle and then find the value that is measured 1 from that angle on that terminal side, or you could find the radius or circle of radius 1 and then figure out where the angle negative 5 pi over 6 is. Either way, you're going to get that same ending spot. All right, how about this one? 5, negative pi over 3. So I'm on this circle of radius 5, and my angle is negative pi over 3. And negative pi over 3 is going to be right here at this terminal side right here. Again, measured down from the initial side. And my radius is 5, so there is my point, my polar coordinate right there. Not too bad at all. All right, now things get a little bit tricky when our r value is 3. Now notice the radius is still 3 because if the radius is the absolute value of your r value, which is going to be 3. So I'm still going to be on that circle of radius 3. And again, my angle is 3 pi over 4. So let's find that angle of 3 pi over 4. So we got 1/4. This would be about right here. Here's 2/4. 3/4 is an angle at a terminal side right about there. Now here is the tricky part when you're working with negative r values. We would think that that angle would be, or that point would be right here at that radius of 3 at 3 pi over 4, but because it's negative, that tells us that we need to go directly across over to here. So we're simply going to reflect across the origin there. So here was the point if it was positive 3, but we are now over here at this point right here. So there is my final coordinate. So again, a little bit tricky there. So just really take your time there to understand this. So I'm finding 3 pi over 4. And I'm going to go onto that circle of radius 3. But because it's negative 3, I'm going to go all the way directly across to this spot right here. A little bit tricky when you're working with a negative r value, but that is how you do it. All right, let's try another one with a negative r value. So first, I'm going to find the angle of 2 pi over 3. So here is 2 pi over 3. Right here's that angle measured in standard position. Negative 1.5. So again, 1.5, positive 1.5 would be right about there. But because it's negative, it's going to get reflected right over to here. So here is the final coordinate for negative 1.5, 2 pi over 3. So again, just be super careful when you're working with negative r values. Let's do a negative r value with the negative angle. Okay, so first, where is the angle negative 4 pi over 3? Well, you could always, depending however you want to find that angle, every kid's a little bit different. Some kids like to count by 6, so this would, of course, be 8, 6. So we got negative 1, 6, negative 2, 6, negative 3, 6, negative 4, 6, negative 5, 6, negative 6, 6, negative 7, 6, negative 8, 6. So here is the angle measured in standard position of -4 pi over 3. Now, we would think that if it was +4, we'd be right here. But again, because it's -4, we're going to come all the way over there. So there is my polar coordinate right here, -4, -4 pi over 3. Now, if you haven't noticed already, when you create a polar coordinate, there are many different coordinates that could land at that exact same point. Now, this is different than rectangular coordinates, because with rectangular coordinates, if you have the point 1, 3, that's it. There's only one point that could go to 1, 3, 1, 3. That's it. But with polar coordinates, we can have multiple coordinates that go to the same point. And let me demonstrate this with this example right here. So I have 4 different polar coordinates, but they all are at the same point. Let me explain here. So looking at this first one, we are 3, pi over 6. So pi over 6 is right here. Here's that terminal side for pi over 6. And then 3 would be right there. There it is. There's that point. But I can also arrive to that exact same polar coordinate using this point, 3, -11 pi over 6. Measuring that negative angle, -11 pi over 6, that's just going in a clockwise direction, going down. So we got -1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6, 6, 7, 6, 8, 6, 9, 6, 10, 6, 11, 6. It's that same terminal side. Pi over 6 and -11 pi over 6 are the same terminal side. And then I have a radius of 3 or an R value of 3. So that's going to end at that exact same spot. Okay, well, I got another angle that could do that as well, or excuse me, another coordinate, -3, 7 pi over 6. Okay, where's 7 pi over 6? Well, that is right here. Here's the terminal side for 7 pi over 6, measured at a positive angle from the initial side. But because my R value is -3, instead of being right here at +3, it gets reflected back to right here, again, where my original point was. So that point is equivalent to the other ones as well. And there's one more. And in fact, there's actually infinite more, but just to give you one more here, -3, -5 pi over 6. Okay, so where's -5 pi over 6? -1, 6, -2, 6, -3, 6, -4, 6. Here's -5 pi over 6. Again, that's just this angle measured just like that, going in a clockwise direction. But again, it's -3 for my R value. So if it was +3, it would be right here. But because it's -3, I'm going to reflect right over to where the original point was, right there. So again, there's multiple different points that can get me, or multiple different coordinates for the polar coordinates that can give me that exact same point, which again, that's different for the rectangular coordinates. So let's go back to this previous example that we're looking at. Let's say, okay, what's another way that I can justify, another way that I can create a polar coordinate that ends at that point? Well, if I wanted to use a +4, well, then I could just use, well, I could do the negative angle that goes directly down there. That'd be -pi over 3. So there we go. 4, -pi over 3 would be the exact same point right here. Or I could leave my R value as +4, and I could go all the way around in a positive direction, which would be 5 pi over 3. So that would also get me to this exact same spot. So again, there's multiple different ways that you could arrive at that particular polar coordinate. Now, we could also take points that are rectangular, like 1, 2, 2, 3, on our XY Cartesian plane, and we can convert them to polar coordinates. Now, how do we do that? Well, we just have to understand the relationship between X, Y, R, and theta. And if you have a good foundation of trigonometry, you should already understand that relationship. We know that R squared is x squared plus y squared. Or you could look at R as the square root of x squared plus y squared. So if you have the x and the y coordinate from your Cartesian plane point, then you could instantly find R just by using that formula. Now, how do we find theta? Well, we know that the slope of that terminal ray is defined as tangent. So tangent of theta equals y over x. So if we know y and we know x, then we could find tangent of theta, and using that information, we can determine what theta is to turn our rectangular coordinate into a polar coordinate. Let's look at some examples right now of how to do this. In this example, we are asked to convert the rectangular coordinate point -1, 1 to polar coordinates. So here we see our xy coordinate plane, xy everybody knows, and we see the point that's left -1 or left 1 and up 1 for the point -1, 1. Now in polar coordinates, we need to find r and we need to find theta. All right, finding r is the easy part. We know that r squared equals x squared plus y squared, and we have our x is -1, so we're going to take -1 squared, plus our y, which is +1, we're going to square that as well. So we get r squared equals 1 plus 1, math's pretty easy there. R squared equals 2, therefore r equals the square root of 2. Now, r, that means we're on a radius of the square root of 2, but r itself could be positive or negative, so we kind of have to determine that in a moment. We got to think about the fact that that could be positive or negative radical 2. Now, next step, again, to make that decision, we got to think about our angle next. So next up is our angle. Now, to find the angle, we know the tangent of that angle equals the y over the x. That means tangent of theta equals 1 over -1, which means tangent of theta equals -1. Now, there are many answers to this equation. There are many answers that theta could be that result in a tangent value of -1. But if we're thinking about on our typical unit circle, 0 to 2 pi, for tangent to be -1, I'm thinking of 3 pi over 4, and I'm also thinking about 7 pi over 4. Now, which one is it? Well, again, think about that point in rectangular coordinate, -1, 1. If I were to think about that terminal side there, it's clearly in quadrant 2, and that would be 3 pi over 4. 7 pi over 4 would be down in quadrant 4, so that's not what we want. So the final value would be, for this, would be radical 2, comma, 3 pi over 4. So again, think about that. That's going to take me to a polar coordinate, angle 3 pi over 4, which is going to put me into the rectangular coordinate of quadrant 2, and then going out onto that value of radical 2 for that radius. But again, hold on a minute. Let's actually think more about this. There's other possible answers because there's multiple polar coordinates that could lead to the same point. If I did want to use that 7 pi over 4, then I would have to use negative radical 2 and 7 pi over 4, because the 7 pi over 4 would take me into the quadrant 4, but then the negative on the r value would reflect me back into quadrant 2 for the rectangular coordinate. So again, multiple different answers that we could get there, but this is primarily the answer that we're going to look for right here. Not to say that's the only answer, but that's going to be the one that most kids are going to jump to or gravitate to. All right, here's another one. Want to convert the rectangular coordinate -3, 0 to polar coordinates. So once again, I have to find r and I have to find theta. So let's find r first. So we know that r squared equals x squared, -3 squared, plus y squared, which is 0 squared. That means r squared equals 9. And then we're going to square root, and means r equals plus or minus 3. Okay, that's pretty simple. Now we got to find our angle. So we know tangent of theta equals y, 0, over x, -3. That means tangent of theta equals 0. Now, where do we have a tangent of 0 value? Well, again, there's infinite answers, but the ones that jump out to me right away are 0 and pi. Well, which one is it? Well, again, look at the rectangular coordinate. If we're thinking about that unit circle, that's at an angle of pi. So I want 3, pi. So if I go to pi and then I go onto a circle of radius 3, I'm going to gather or create that particular point that has a rectangular coordinate of -3, 0. We could also convert points the other way. We could take a coordinate point that's in polar coordinates and we can convert it to rectangular coordinates. So in polar coordinates, we have r and we have theta, and we want to convert that to rectangular coordinates x, y. This is actually really simple. We know through the relationship of x, y, r, and theta that x equals r times cosine of theta and y equals r times sine of theta. So all we got to do is take our r and our theta from our polar coordinate point and plug them into the formula to determine what x and y are, and then all of a sudden we'll have our rectangular coordinates. Let's look at some examples right now. In this example, we want to convert the polar coordinate point 3, 5 pi over 6 to rectangular coordinates. So first, in a polar coordinate grid, I have the point 3, 5 pi over 6 labeled. Okay, now the conversion here is pretty easy. X equals r times cosine of theta, and y equals r times sine of theta. So really not too difficult here at all. So to find the x coordinate, I'm going to take 3, that's my r value, times cosine of 5 pi over 6. And to find the y value, I'm going to take 3 times sine of 5 pi over 6. Okay, so first thing I got to do is figure out what is cosine of 5 pi over 6. So hopefully you're pretty good with your unit circle. Some kids like to draw a little picture if they need to find where that is. But the cosine value is negative radical 3 over 2. So we have 3 times negative radical 3 over 2, which gives me a final answer for that x value of negative 3 radical 3 over 2. All right, now for the y coordinate, we're going to take 3 times sine of 5 pi over 6, and sine of 5 pi over 6 is 1/2. So our y coordinate is 3/2. So in rectangular coordinates, we have negative 3 radical 3 over 2, comma, 3/2. And that should make complete sense. If I were to overlay a rectangular coordinate grid on top of this polar coordinate grid, that's exactly where that point would be. It would be left negative 3 radical 3 over 2 and up 3/2. All right, let's take a look at another example. Here we want to convert the polar coordinate point negative 2, 5 pi over 4 to rectangular coordinates. So first, make sure we understand that that is exactly where this point is located on the polar grid. 5 pi over 4 is this terminal ray over here, but because it's a negative r value, it flipped me into that top value right here where I ended up on that circle of radius 2. All right, so once again, my x coordinate is going to be the r, negative 2, times cosine of my angle 5 pi over 4. My y is going to be negative 2 times sine of that 5 pi over 4. All right, this isn't too bad. So let's see here. What is cosine of 5 pi over 4? Well, that is negative radical 2 over 2. So when I do the math there, the negative times the negative makes a positive. My 2's are going to reduce, and I just get radical 2. Now for my y value, I also have negative 2 times, well, sine of 5 pi over 4 is also negative radical 2 over 2. So again, the negatives make a positive and the 2's reduce to 1, and I just get radical 2. So the answer here would be radical 2, comma, radical 2, which would definitely be in quadrant 1. So if I were to overlay a rectangular coordinate grid on top of this polar coordinate grid, it would make complete sense that that point is at positive radical 2 for my x, positive radical 2 for my y. All right, here is another example. Convert the polar coordinate 10, 5 pi over 3 to rectangular coordinates. So here we see 5 pi over 3 right here. Here's that terminal ray for 5 pi over 3. And then we see that that point is all the way out there in a circle of radius 10. All right, so my x value is going to be r, 10, times cosine of 5 pi over 3. My y value is going to be 10 times sine of pi over 3. Sine of 5 pi over 3. All right, so now I just got to use my unit circle to know what cosine of 5 pi over 3 is. So cosine of 5 pi over 3 is 1/2. So I get 5 for my x coordinate. And then for my y coordinate, I'm going to take 10 times sine of 5 pi over 3. Sine of 5 pi over 3 is negative radical 3 over 2. So that's going to become negative 5 radical 3 when we do the math. So the point is 5, comma, negative 5 radical 3 in rectangular coordinates. All right, let's do another one here that's essentially the same thing, but there's a little bit of a trick to it. So the point P is in the polar graph below. If the point P is rotated pi over 2 counterclockwise to a new point, what is the rectangular coordinate of this new point? All right, so the first thing I'm going to do is recognize this point P here, and I'm going to try to figure out what it is. So first off, it's an r of 4. So we see it's on a radius of 4. So that's going to have a r value of 4 there. And then that angle is 5 pi over 6. Okay, so they want me to take this point and they want me to rotate it pi over 2. So when I rotate it, it's still going to have an r value of 4. That's not going to change. But they want me to rotate it pi over 2. Now I'm going to convert pi over 2 to 3 pi over 6. That way since my point is at 5 pi over 6, I want to have that common denominator. It makes it a little bit easier for me to think about rotating it. And they want me to go counterclockwise. So that means I'm going to start going down. So here it is. So if I move it to here, that would be moving it 1/6. Moving it to here would be 2/6. Moving it to here would be 3/6. So here is that final new point that was taking the original point P and rotating it counterclockwise 3 pi over 6, which is pi over 2. So that new coordinate there is going to be 4 comma 4 pi over 3. If I'm thinking about what this terminal side right here is, hopefully you guys recognize that that is 4 pi over 3. All right, so now that I determined where that new point is as a polar coordinate, now I have to convert it to rectangular coordinates using x equals r, 4, times cosine of 4 pi over 3, and y is going to be 4 times sine of 4 pi over 3. All right, so let's see here. Cosine of 4 pi over 3 is negative 1/2. So 4 times negative 1/2 is negative 2 for my x-coordinate. And sine of 4 pi over 3 is negative radical 3 over 2. So when I multiply, that's going to be negative 2 radical 3. So the rectangular coordinate for this new point that's got rotated is going to be negative 2, comma negative 2 radical 3, which again should make sense because if your x and y are both negative, you're going to be down there in quadrant 3, which is exactly where this polar coordinate is. Lastly, we want to look at complex numbers and how we can look at complex numbers in the complex coordinate plane and how they can be converted to rectangular coordinates and polar coordinates in those respective planes as well. A complex number can be understood as a point in the complex plane and can be determined by its corresponding rectangular or polar coordinates. When the complex number has the rectangular coordinates a comma b, it can be expressed as a plus bi as a complex number. When the complex number has polar coordinates r comma theta, it could be expressed as r times cosine of theta plus I times r sine of theta. So when we have our a and our b value, we could look at a, that's our x-coordinate, as r times cosine of theta. And then we have our b, that's our y-coordinate, we could look at that as r times sine of theta. So if we have a complex number, a plus bi, in rectangular coordinates, that is a comma b, or x comma y. And then in polar coordinates, we can convert that to a complex number as well, using r times cosine of theta plus I times r times sine of theta. Let's look at some examples right now of converting complex numbers to rectangular coordinates and polar coordinates. In this example, we are asked to convert the complex number 6 plus 6i using polar coordinates in the form r cosine of theta plus I times r sine of theta. All right, so here's what we know. We know that if this is our complex number, that in rectangular coordinates, that would be 6 comma 6. So our a value is the 6 and the b value is also 6. So the rectangular coordinate would be a comma b. That means my rectangular coordinate for this complex number is 6 comma 6. Okay, so now what I have to do is I have to find r and theta using this x and y. That way I could put this into polar coordinate form. And that's actually pretty easy. So here's what I know. I know that r squared equals x squared plus y squared. Therefore, r squared equals 6 squared plus 6 squared. R squared equals 36 plus 36. And r squared equals 72. Take a square root and a square root. R equals, well, 72 can be reduced. That's going to be 6 radical 2. All right, there we go for that first part right there. Not too bad to find r. Now to find theta. I know that tangent of theta equals y6 over x6, which means tangent of theta equals 1. Now, where is tangent of theta equal to 1? Well, that's going to happen at pi over 4 pretty easily there. So now that I have my r and my theta, I could go ahead and put this complex number into polar coordinates. So it's going to look like this. It's going to be 6 radical 2 times cosine of pi over 4 plus I times 6 radical 2 times sine of pi over 4. There it is right there. Pretty easy, not too bad at all. Now, one thing we could do with this problem is we could easily check our work by just figuring out what cosine of pi over 4 and sine of pi over 4 is. So again, if we have 6 radical 2, and I hope everybody knows cosine of pi over 4 is radical 2 over 2. Now all I have to do is multiply that out, and that's going to be 6 times 2 over 2. Radical 2 times radical 2 is 2. That's going to be 12 divided by 2, and that's going to be 6. Oh, yeah, that's the 6 I had right here. Same thing back here next to the I. So this is going to be 6 radical 2 times sine of pi over 4, which is also radical 2 over 2. Multiply that, we get 6 times 2 over 2. 6 times 2 over 2 is 6. Oh yeah, that's the 6 I got right there. So it's pretty easy to check my work to make sure that my polar coordinate form for that complex number is in fact equal to the complex number itself. All right, let's do another example here. Convert the complex number 1 minus radical 3i using polar coordinates. Okay, so if this is my complex number, that means my rectangular value must be 1 comma negative radical 3. That's my a and my b value. A is 1, b is negative radical 3. All right, so now I have to find my r. So r squared equals x squared, that's 1 squared, plus y, negative radical 3 squared. So r squared equals, whoop, I messed that up a little bit. Sorry for my messy handwriting. R squared equals 1 plus 3. 1 squared is 1. Negative radical 3 squared is 3. So r squared equals 4. Therefore, r equals 2. Okay, not too bad. Now to find theta. Well, I know that tangent of theta equals my y value of negative radical 3 over my x value of 1. Therefore, tangent of theta equals negative radical 3. Now, thinking about your unit circle, where is tangent of theta equals negative radical 3? Well, there's lots of angles where tangent of theta equals negative radical 3, but just a couple that come to mind pretty quickly are 2 pi over 3. We could even have 5 pi over 3. We could even do negative pi over 3. Now, which one is it? Well, it can't be 2 pi over 3 because 2 pi over 3 would be in quadrant 2. And in quadrant 2, x is negative, y is positive. And if I'm thinking about my rectangular coordinate right here, that's clearly going to be down here in quadrant 4 where the x is positive and the y is negative. So I don't want to use 2 pi over 3 as my angle. Now, I could use 5 pi over 3. That's definitely going to be down there in quadrant 4. But I could also even use negative pi over 3 as well if I really wanted to. That's just going to be the same terminal side, just going down clockwise instead of around counterclockwise. So we'll use the 5 pi over 3. So in polar form, we have 2 times cosine of 5 pi over 3 plus I times 2 times sine of 5 pi over 3. Not too bad there. Hopefully that all makes sense. Now, I actually want to go back to talk about how I said that you could not use 2 pi over 3. Well, you could actually, if you wanted to, you would just have to make your r value negative. Because if I wanted to start up here at 2 pi over 3, which is up here in quadrant 2, but then I wanted to come down into quadrant 4, then I would simply have to make my r value negative in the polar coordinate system. So as if I made the r value negative 2, and I used 2 pi over 3 for my theta, then I could make this work in the polar coordinate system. So there's a lot to think about with polar coordinates here, but hopefully that general idea here for this problem made sense.